Well, guys, good morning. We're going to get started. There is a very, very, very real chance that today is going to be an absolute disaster. But you also know from talking previously as we were chatting, guys, that we really want to be done before spring break, right? But we've got 1 or maybe 2 days that we may have to either do on Wednesday or find another way to address. Well, guys, today what we're going to do, and I may as well pull up the notes, we are going to start chapter 16. I know you've done chapter summaries. We'll talk later. We're going to start into chapter 16 with an overview of acids and bases. Now, guys, normally this day gets broken into two simply because people want to talk a lot about it, because it's all the stuff that you learned in general chemistry last year that we didn't really get to talk about because we had to skip through it because it was general chemistry. All of that to say, guys, I think we can buy back a day today by doing this all in one day. And this sounds horrible, but the reason I think we're going to be able to get away with this is frankly because you're going to be clueless. Because, guys, normally, as I said, this day takes a really long time because students are like, oh, I didn't understand that last year. Let's talk a lot about it. But, guys, you learned this stuff in like 2 screencasts locked in your basement last April. So the chance that you know much of this at all, or the chance that you found any of this intriguing enough that you're going to be like, oh, now can I ask all my questions? That's probably not going to happen, which is sad. But guys, we're going to try this. What I'm not doing is saying don't ask questions. Quite the opposite. If you have questions, ask. And you know what? If it turns out we need to break up the day, we'll break up the day. But let's see how it goes. With that said, guys, another thing quickly. I was going to hand back to you your tests today, your previous tests. I didn't get them done. Frankly, that's not an issue for you. It's an issue for me. What it means is it just gives me less time to grade your rewrites. To be honest with you, the parts that I have graded, you guys have done very well. As a group. There's always outliers, right? But for the most part, you guys have done great, which means the rewrites are going to go fast. I'll give them to you Monday, and then we will turn them back in on Thursday, which gives me 24 hours to get them graded, but we should be okay. So, guys, with that said, acids and bases, you ready to go? Grab something you can write with, because there's definitely stuff that you want to be writing down. Guys, please, and I don't know if we've talked about this before, amazing research that says the very best way for you to learn, and leverage this in college, the very best way for you to learn is not to take notes, but to have the notes and then jot your thoughts and questions into the notes. Guys, when you get to the university level, many of your professors will actually sell you bound copies of their class notes. Buy them. It is so worth it to have your teacher's class notes because they don't slow down. They don't answer questions. They just go 1,000 miles an hour, and when the bell rings, they're done. It's so nice to have notes in front of you. So guys, with that said, maybe you could try this out today, but you do need something to write with. So guys, let's get started. So fundamentally this, when we talk about acids and bases, guys, there's 3 ways to think about acids and bases, and they're named after the people that came up with them. Arrhenius, Bronsted-Lowry, and did you pick up the last one? Lewis. We're not going to do Lewis. Guys, Lewis is coming when you take organic chemistry, because Lewis is all about the movement of electrons, Lewis dot structures, right? Guys, that becomes wonderfully important your sophomore year in college when in organic chemistry you learn to do what are called electron pushing diagrams. They're horrible, but that's coming. What you need to know are the Arrhenius and Bronsted-Lowry definitions. And guys, this is the Arrhenius definition of an acid and base. Let's say this right now. This only works for strong acids and strong bases. That's not in your notes, so you may want to write it down. Guys, the Arrhenius definition only applies to strong acids and strong bases. Guys, if you have not committed the strong acids and bases to memory, which I know you haven't because you were never held accountable for it, you need to do that. But guys, let's talk about it. Make the connection from the little bit that you remember. Why does this only apply to strong acids and bases? Go ahead, Annika. That's true, but completely dissociate into what? What are the strong acids and bases? They're aqueous. Am I squeezing water from a rock? Guys, the strong... go ahead, try it. Exactly. So guys, this is the idea. Everything that you said was right, but the bigger idea is this. The strong acids, HCl, HF, HBr, HNO3, H2SO4, HClO3, and HClO4, they all have hydrogens bonded in such a way that, as Annika said, they're strong electrolytes. They all give away hydrogens and therefore increase the concentration of hydrogen. But Brayton got the more subtle thing. Guys, in order to be a strong base, you've got to be a metal atom bonded to hydroxide. Guys, strong bases by definition bring hydroxide to the table, and so long as we're talking about it, it's lithium through cesium. We don't count francium because it's too radioactive, and then it's calcium down. So guys, it's lithium through cesium, calcium, strontium, barium hydroxides. Those metal hydroxide salts are the strong bases, and they all bring OH to the table, and therefore they bring OH that increases concentration. You guys good? Okay. Then this is the definition that we are going to use more frequently, and this is the Bronsted-Lowry definition. And guys, in the Bronsted-Lowry definition, it's all about the movement of protons. So how does this connect? Guys, you want to draw arrows and make these connections. So guys, how does the Arrhenius and the Bronsted-Lowry acid definitions line up? Because frankly, they're exactly the same. What's the connection between the two, Max? Boom. Yeah, because guys, this is this. Hydrogen ions are protons, and consequently, the Bronsted-Lowry definition and the Arrhenius definition are exactly the same. Guys, that is not true, kind of, for the base definitions, but it is very close, because check this out. So guys, if you've got an OH, guess what that OH wants to hook up with because it's negative? Protons, right? Which then gives us this definition. So they are complementary, but they're not exactly the same because there are substances other than OH that can take in protons. An example of that would be NH3. NH3, when you dump it in water, actually forms NH4 plus and hydroxide. So guys, this is a base and it doesn't contain OH. It's a base because it does accept hydrogens from water, but notice when it does, it turns water into hydroxide. So these are complementary definitions, but they're not the same definitions. So guys, let's pause. If you need to jot any of that down, you certainly can. But guys, questions fundamentally about Bronsted-Lowry or Arrhenius acid-base definitions? You guys okay? Are we good? Okay, so we're going to move on. All right, so guys, as we move on then, we need to start talking about how these things interact when they go into water. So guys, so much of the chemistry that we're going to do is aqueous-based, acid-based chemistry. So turning the page, we need to talk about specifically what do acids do when they go into water. And guys, when acids go into water, whether it's Bronsted-Lowry or Arrhenius, acids are simply sources of protons. But then, guys, these protons are wildly attracted to the unbonded electrons on water, and when those bond together, they turn into this dude, which is called hydronium ion. So, guys, what you're going to find as we move forward in the year is that we are going to talk about acids in water either as sources of hydrogen ion or sources of hydronium ion, and we are going to use these interchangeably. So you're going to get really strategic about this. You're going to be like, okay, this is an acid, let's talk about hydrogen ion. Or this is an acid, let's talk about hydronium ion. And guys, you're going to learn to use these interchangeably. I know that that's weird, so do this with me. Guys, on your notes on that page, you know what's coming, right? What are we about to draw? A beaker. Draw yourself a beaker, and then in that beaker, put some water, and then in that beaker, let's add some HCl. Guys, in that beaker, including water, write the species that you will, don't draw them, just write them. Guys, what are the species that are in a HCl solution? Some of you are going to find this interesting. Ready? So we've got water in here, yeah? Well, yeah, because that's the blue line. That's the water. And then, guys, when we put HCl in water, how do we know that it completely dissociates? Because it's a strong acid. But, guys, here's the thing that's weird. It doesn't just break apart into water. It reacts with the water. So when this breaks apart into hydrogen ion and chloride ion, the chloride ion is a spectator. It's just chilling in solution. But guys, where does the hydrogen ion go? To the water, and it forms H3O+. Now guys, here's the question. How much hydrogen ion is in that beaker? How much hydrogen ion is in that beaker? There's none. Make sure that makes sense. Guys, there is no hydrogen ion in an acidic solution. All of the hydrogen ion that the acid gives away latches a hold of water and turns into hydronium ion. There is no hydrogen ion in solution. Yeah, and that's exactly right. So if you get an acid burn and you're like, the acid's burning me. It's not. It's the hydronium ion that's burning you. Yeah, so, and if you think about it, it's kind of weird, but all acids kind of react the same, right? Spill sulfuric acid on this arm and hydrochloric, and it looks a lot the same because both of them are simply sources of hydronium ion. The strength of an acid or the danger of an acid is dependent on how much it makes, but they all just make hydronium ion. Yeah. Yeah, so keep going. No, so it just wouldn't dissolve. So great question. And actually the answer is even more interesting than you know, but let's talk about it. So what if you saturated the solution? Well, by definition, saturated means no more will dissolve, right? In this case, it's actually a two-part story because it's no more will dissolve and therefore no more will react to form hydronium ion. So what happens to the extra HCl that won't dissolve? And this is the thing that's interesting. All of the strong acids are molecular gases. So HCl in its non-dissolved form is actually a gas. And all 7 of the strong acids are gases. And so the HCl that doesn't dissolve will actually just off-gas and go away. Yeah, yep. You guys okay? So now this becomes the weird part, because guys, you now understand this idea that there is no hydrogen ion in an acidic solution, but guys, that then makes this statement kind of weird. So guys, we are actually going to use these interchangeably. So when we talk about what acids do in water, many times we're going to say acid makes hydrogen ion. No, it doesn't. It makes hydronium ion. But guys, sometimes it's not important for us to think about the water, so we're just going to treat acids as if they make hydrogens rather than making hydronium. So guys, I know this seems weird right now, but just understand we're going to use these interchangeably. But anytime we write down hydrogen, we're really understanding that it's hydronium. It's just not important for us to think about the water. Is that okay? All right. So guys, moving on again then, let's keep digging into these ideas. So now that we've got some fundamentals about acids and bases, guys, just be honest with me. Do you remember anything about conjugates that you learned? Do you really? Yeah. Do you really? Oh. Okay, realize that what you just said is you actually learned something during COVID. Really? All right. So guys, let's review. Last year, and I love that you actually feel like you remember this. Guys, last year, conjugates were a means to an end. Find the conjugates. Guys, this year, we are literally going to do more chemistry thinking about conjugates than we are thinking about the original acids and bases. Conjugate chemistry is a huge thing that we're going to do in the next couple weeks. So, with that said, guys, right now, you just need to be able to identify acids and bases and conjugates. So guys, fundamentally, it goes like this. A conjugate acid is the particle that is formed when a base gains a proton. Now guys, think about that. Base gains a proton. Isn't that what bases do? But now guys, when the base gains a proton, this base now has an extra proton. What can it do with that proton? Give it away. What does that make it? It's now an acid. Do you understand the idea? So the idea is that the conjugate acid is the base plus a proton. When the base gets the proton, it's now got an extra proton. It can give it away and it functions as an acid. So we would say it this way. The base plus the proton is the conjugate acid, and it can function as an acid. Then the conjugate base is the thing that's formed when the acid loses a hydrogen. It's now hydrogen deficient, and if it can get that hydrogen back, it's now functioning as a base, making it the conjugate base. Does that sit okay? Yeah. That's exact, and I know that you don't remember that, but that is the bridge that we used last year to teach you equilibrium. We actually learned acids and bases the first day, and then the second day we came back and said, what does that mean, that it's a conjugate acid and base? Well, it really is an acid and a base, and if these react together, they turn into this, and that was the first time you saw the double-headed arrow. Yeah, go ahead. Yeah, well, so long as it's in water. If it's in water, yes. And we're going to ease into this, but this is what makes acid-base chemistry challenging. Because so think about all the aqueous chemistry that we've already done, right? The water was just assumed to be there, and it was like a playground where all the ions mucked around with each other. The thing that's weird is in acid-base chemistry, the water gets involved in the chemistry. The analogy that I use is it's kind of like kids playing on a playground, but the playground's not just the surface, the playground's part of the game. And that's really what's going on, is that the water gets involved. And so that's one of the things that makes this hard, is we've got to include the water in our thinking. And if water is included, then yes, it does both. It accepts hydrogens and increases OH. Go ahead. No, great question. And I love that you know amphoteric. So let me repeat your question. So do acids and bases at some level behave amphoterically, which means they can be both? And the answer is not if they're strong. You ready for an interesting thought? So guys, did you understand Annika's question? Because it provides a really interesting thing we're going to talk about eventually, so let's do it now. So she said, and here's the answer to your question. Do all acids and bases have the ability to be amphoteric, functioning in both directions? And the answer is, not if they're strong acids and bases. So let me show you. So for example, we've already talked about it, so let's just do it again. HCl, right? And so HCl breaks into hydrogen and breaks into chloride. Guys, where does HCl break into hydrogen and chloride? In water. But why did we not include the water? Because it's not important in this context. We could have just as easily done this and added the water, and then guys, our products would be hydronium ion and chloride ion, but mentally we're going to treat these the same. So, with that said, why don't we just look here? So, Annika, your question was, can they be amphoteric? And the answer is no. The reason is because chloride is a worthless conjugate base. Please don't use the word worthless on the AP test. We use the term of negligible strength. We're going to talk later. But here's the deal. Guys, check this out because this is actually interesting. Guys, why is HCl a strong acid? You know that there are 7, but guys, don't miss this. Why is HCl a strong acid? The answer is because chloride is a worthless base. Let that rattle around in your noggin for a minute. Guys, why is HCl a strong acid? Because chloride is a worthless base of negligible strength. Chloride is not able to grab a hold of protons. As a result, this cannot go backwards, and that makes this a strong acid. So now we can talk about the whole answer to your question. So can acids and bases behave amphoterically? And the answer is not the strong ones, but all the rest of them, yes. And what makes the strong acids and bases strong? Check this out. Their conjugates are worthless. Does that really make sense to you? Because that's a big idea. Guys, why are the strong acids and bases strong? Because their conjugates are worthless. They can't go backwards. Yeah. Brilliant. Yeah, so that's exactly right. So acetic acid is this dude, and it breaks into protons and acetate ions, but the acetate ion is actually a fairly good base. It does a pretty nice job of grabbing onto protons. And when it does, it drives the reaction in this direction, and it makes it equilibrium. So the idea, and this is where we're going to go after the weekend, we're actually going to figure out the relative strength of this acid, the relative strength of that conjugate base, and we're going to use those numbers to figure out which side the equilibrium lies on. But that's exactly right. Go, yeah. Yeah, so amphoteric, man, we're going to get to it in a minute. It means has the ability to be an acid and a base. A great example of that is the bicarbonate ion. So bicarbonate contains a hydrogen, which means that it can give away that hydrogen, and when it does, it turns into protons and carbonate ion. But bicarbonate also has the ability to grab a hold of a proton, and when it does that, it turns into carbonic acid. So carbonate has the ability to both lose and gain a proton, and that's what amphoteric means. It can function as both an acid and a base. But you're going to find out in a couple days, it's better at one than the other, and we're going to quantify that by calculating what are called Ka and Kb values, and then we'll know which one it does more readily. So, guys, how are we sitting? Please. Yeah, why is it worthless? And the answer is because adding that additional electron gives it the electron structure of a noble gas, which stabilizes it. Yeah, and actually, if you ready for, you guys are right, there's so much going on. But if you look at the strong acids, HCl, HBr, and HI, those are all strong acids. The reason is because these conjugate bases are stabilized as noble gas structures when they pick up the electron. The other ones, HClO3, HClO4, NO3, and SO4, are all resonance stabilized molecules. Remember delocalized pi bonding? If you draw the Lewis dot structures for those things, so the other strong acids are H2SO4, HNO3, HClO3, and HClO4. And if you pull the hydrogens off of these things and draw the Lewis dot structures of the conjugate bases, they all resonate. And because they resonate, it actually allows them to be stable without that hydrogen, and they can't go backwards. Yeah, did we ever use the term resonance stabilization? resonating actually stabilizes molecules. Exactly, and that's why they can't go backwards. Yep. You guys okay? Okay, let's keep going, y'all. So it sounds like you may be okay with, guys, did you catch this? Down at the bottom of this page of notes, this important rule that Annika got us thinking about. So guys, when we think about conjugates, guys, the stronger an acid is, the weaker its conjugate. Up to this limit that a strong acid has a worthless conjugate base and a strong base has a worthless conjugate acid. That's what makes them strong. So we've introduced the idea here, but we talked about it at great length. Does that sit okay? Okay, so guys, with that said, then let's do this. Let's start talking about, well, hold on. Do I not have an example? Let me, oh, there it is. Guys, that's in the wrong place. These slides are out of order. That's really strange. So guys, switch the next slides. Instead of going to strong acids and bases, let's go here. You have it in your notes. Do you see how we just jumped down a slide? We'll go back. Guys, try at least one. So in this reaction, identify the acids and the bases and the conjugates. Just scratch it. Just make sure you're okay. And by the way, guys, this can get a little weird. The acid and base are always on the left, and the conjugates are always on the right. How you guys doing? You okay? Good? Okay, so the way that, and guys, sometimes these will get confusing, so let's talk strategy. What I like to do is I like to go to the first substance, and I like to cover over the hydrogen. Well, let's do it wrong. Imagine that water was our first substance, and I cover over the hydrogen. What am I left with? OH. But there's no OH over here, which means that is not my hydrogen loser. Then I come over here and I cover this, and I'm left with NO3. And there is that, which tells me that this is my hydrogen loser, so this is my acid. And guys, once you identify that, it all just falls together. If one is your acid, the other is the base, then for me to figure out the conjugates, I go to the acid, remove the hydrogen. What's left is the conjugate base. The other is the conjugate acid. Do you really remember that? Is that okay? I know that's fast, but some of you are saying I remember it from last year. Good? Okay. So guys, let's do this then. This is kind of back to Chandler's question. Now if we look at this dude, and I'll just do it, NH3 turns into NH4. So this is our hydrogen gainer, so that's our base. This is our acid, making this our conjugate base and our conjugate acid. Is that okay? So now, Chandler, to your question, what's up with water? Is it an acid or is it a base? Well, here, acid plus base. So here, guys, it's a base, and here's it's an acid. So which one is it? It's both, making it amphoteric. Is that okay? So guys, let's make a point then really quickly. We talk about these things very empirically. We say HCl is an acid. We say NH3 is a base. But guys, don't miss this. This is really a critical thought. When we say that something is an acid, all that means is more acidic than water. And when we say that something is a base, what we're really saying is more basic than water. So guys, water becomes our fulcrum for our teeter-totter, if you will. If something's an acid, it just means more acidic than water. If something is basic, it means more basic than water. So when you put HNO3 into water, why does it give away hydrogens? Because HNO3 is better at giving away hydrogens than water. And guys, when you put NH3 in water, why does it take in hydrogens? Because this is better at taking in hydrogens than water. Guys, don't miss that point. Just a second. This is critical. Guys, when we talk about acids and bases, it's always relative to water. So this is an acid because it's better at giving hydrogens than water. This is a base because it's better at taking hydrogens than water. Water is our 0 point in this scale. Yeah. That's where we're about to go. And you're about to have that's exactly why water is in the middle. Yeah. No. That's a great, and that's not off topic or arbitrary. That's where we're going next. So why, you're exactly right, Braden, the water's in the middle, but why? And let's talk about it. Go ahead. Yeah? Bingo, exactly. So when HNO3 is the acid, it simply means more acidic than water, so water becomes the base. Yep. You guys okay? So guys, let's do this then. Let's skip up to the previous slide. Oh wait, for me it's down now because I moved it. So guys, as we then talk about this idea of acids and bases, we need to talk about strength as a transitional thought. The strength of something is literally its ability to do what it does, either give away or take in things. So guys, again, when we talk about the strong acids, they completely protonate in water. There are 7 of them. The weak acids, as I think Braden or maybe Matthew got us thinking, like acetic acid, only partly ionizes in water. And then guys, we've said this: the stronger the acid or the base, the weaker the conjugate. Is that okay? Okay. So now, guys, let's drill into the question that you were talking about. And you really are going to have an aha moment. So, guys, which one is it? Is water an acid or is water a base? Yes. But, guys, if you've never thought about why, consider this. If you draw the Lewis dot structure for water, it looks like this. What does this make water? It's a proton. That's an acid. What does this make water? It's an OH. It's a base. So your question, Ronnie, was why is water in the middle? Is it arbitrary? Is it because water is the most plentiful substance on Earth? And the answer is no. The reason water is in the middle of acid-base chemistry is because literally it's an acid because it has a hydrogen, and it's a base because it has an OH. Guys, to me that feels like a little more than coincidence, but that's a whole different conversation. But if you just settle here for a minute, that the very most plentiful substance on Earth is perfectly and simply the exact representation of the most important molecule type that there is on Earth, an acid and a base. Guys, literally you are written in acid because you're written in DNA, deoxynucleic acid. Guys, DNA and RNA, the A in DNA and RNA is acid. Guys, the very fundamental communication strategy for the things that make us up are acids. Guys, these are huge, these are important, and the very literally thing we're swimming around in is exactly an acid and a base. That to me is cool. Yeah. 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 Yeah, hold on, let's get there in just a second. It's a great question, but we need to start talking about strengths, which we won't be ready to do until we do pH. But we'll get there. So guys, let's make sure we're clear on this. When I put HNO3 in water, follow this logic because this is brilliant. When I put HNO3 in water, which way do the protons move? Left to right or right to left? Let's do it again. When I put HNO3 in water, which way do the protons move? To the right or to the left? to the right. Because HNO3 is an acid, the protons latch on here, and we end up with hydronium ion forming. Guys, the question is why? Why do the protons move to the right? Because nitric acid is better at giving away protons than water. You understand that now? When we say something is an acid, we simply mean more acidic than water. So guys, the reason the protons move to the right is because the HNO3 is better at giving away protons than water. So guys, what if we do this? What if we throw ammonia in water? Now which way do the protons move? Still to the right? Because guys, NH3 is a base. And now the protons move in this direction. Why? Because NH3 is better at taking in hydrogens than water is. So NH3 is a base. But again, we say that only relative to water. Is this starting to come together? Because now, guys, it brings up a really interesting question. What if we put water in water? Because water, guys, is actually a solution of water dissolved in water. And guys, when water gets together, guys, we actually have an equilibrium that is established. This is what is called the auto-ionization of water. And guys, what is going on in this is this. Let me switch colors. In a bucket of water, guys, just spontaneously, in a bucket of water, when these water molecules bump into each other, in a bucket of water, on occasion, when these things bump into each other, these water molecules hit, and one of them goes, here, I'll take that. And then this guy turns into a hydronium ion, and this guy turns into a hydroxide ion, and literally water ionizes other water molecules, and we end up with some hydronium ion and some hydroxide ion in any bucket of water. Guys, the question is this: how much of this do we end up in a bucket of water? Well, guys, we're going to figure it out. Do you understand the chemistry we're talking about? So let's think about this as chemists think about this. Guys, write the equilibrium expression for this process. Just do it in your notes right now. Write the equilibrium expression for this process. Or is it already there? Did I put it in there? I can't even find where we are. Hey, there we go. Oh, I left you space. Guys, write the equilibrium expression for this reaction. Don't screw it up. Because you're going to screw it up. No, the equilibrium expression. Not the balance, the Kc value. Oh, yeah, those Kc things. Write Kc. Products divided by reactants. Braden, we're getting dangerously close to your question. You're going to love the answer. So guys, for the sake of time, I'm going to catch up with you. And by the way, for those of you that hesitated and said, wait, equilibrium expression. Guys, that's what we call Kc expressions. They're equilibrium expressions. So we go like this. Kc is equal to products, which is HNO3, or HNO3, H3O, hydronium ion, hydroxide ion, and then guys, you ready? Get a little risky here. Water squared? Water squared? Is that okay? Okay, but guys, it's wrong. Okay, this is a heterogeneous equilibrium. What never goes in equilibrium expressions? Solids and liquids. So guys, get rid of the water, and now we're left with this. I know. But guys, check this out. What you just wrote is the Kc expression for what takes place inside of water. So we don't call this Kc, we call this Kw. Guys, grab your AP equation sheets and find it. What we just did is we wrote what is now called a Kw expression. Does anyone have one I can look at? Okay. Here, I'll get two. One for you and one for me. I know. All right, so guys, how far down is it? Oh wow, it's clear down there. Fifth one down. You see it down there? Kw is hydrogen times hydroxide. We all good there? Now guys, check this out. This is interesting. Follow this logic and you'll never forget this. This is cool. So guys, this is what we're saying. Let me erase this so I can plug this in. Like so. So guys, what we've done is we've written the equilibrium expression for the reaction that's up above. So let's check this out. So what we got is one water reacting with another water. When it does, a hydronium and a hydroxide ion are formed. Does that make sense? Then let me ask you this question. If this is true, then what has to be true of the molarities for these two things? They must be the same. Do you see why? So guys, where does hydronium and hydroxide come from? From water molecules running into each other. And when two water molecules run into each other, they make one of these and one of those, and they will always be equal in water. Does that make sense? But now guys, here's the thing that's interesting. You can measure them. And guys, when we measure the concentration of these two ions in solution, guys, write this down with me. It's not in your notes. When we measure the molarities of these, guys, the molarity for both of these is 1 times 10 to the negative 7th molar. They are not only equal, they are both 1 times 10 to the negative 7th molar. Now guys, pull out your mad algebra skills. What do you get when you multiply 1 times 10 to the negative 7th times itself? 1 times 10 to the... Do you see that in the AP sheet? Guys, find that in the AP sheet. That value, Kw, is constant. This is an equilibrium constant. And so long as the temperature doesn't change, that doesn't change. The Kw value is 1 times 10 to the negative 7th, and that doesn't change, and we're going to leverage that in just a minute to do some math. But are you all settled on the idea? Now guys, did any of you have the aha moment relative to these molarities? Because I would propose to you that you came into here knowing that molarity. Do you see why? Guys, what's the pH of water? That's those 7s. So guys, the idea is this. You may want to write this down. pH is equal to the negative log of hydrogen ion concentration. Plug in the hydrogen ion concentration. It is the negative log of 1 times 10 to the negative 7th. And guys, let me just do the math for you. The answer is 7. This is why the pH of pure water is 7. It's because the auto-ionization of water creates a hydronium ion concentration of 1 times 10 to the negative 7th. And that, as Braden got us thinking some time ago, is also why water is in the middle. That's why it's not only our foundational turning point for acid and base definitions, it's also why the pH is 7. So guys, we learned a lot of stuff. We learned that water ionizes itself. We learned that when it does, we get equal concentrations of hydronium and hydroxide. We learned that those concentrations at room temperature are 10 to the negative 7th molar, giving us a product, or Kw, of 1 times 10 to the negative 14th. And all of this is based on the idea that water's pH is 7. Anything there you want to talk about? You guys okay? That's a lot of stuff, right? Yeah.
Well, kind of going back to when we were talking about what makes an acid better than
Stronger? Yeah. Oh, better. Yeah, better is a good word. Okay.
Does that go back to the anion stable, or what does make something better?
Great question. So what is it that fundamentally makes something electron or proton hungry? And there's actually electronegativity, right? Electronegativity is a measure of an atom's ability to steal other electrons. There's an analog to that, which is sort of like a molecule's ability to attract protons. And it's not as clean. Think about what leads to electronegativity. It's the strength of the nucleus. It's the shielding of the electrons. Things play into it, right? There are also ways to quantify a molecule's desire to steal protons. And it depends upon things like polarity and electronegativity and the availability of unbonded electrons. But we can quantify it. All we need to know is more or less than water. But they are quantifiable if we choose to do it. No, not in here. Not in here. No. But what we will have, and I'll bring it up in a minute, is a chart of what things are more or less proton hungry than water. But rather than need to predict which is which, we quantify it by looking at what are called Ka and Kb values. And we'll get into that next time. Anything else here you want to talk about? Go ahead, Max. Say that again. Yes. Absolutely. Oh my gosh, absolutely. Yeah, that's exactly what that means. I don't remember which direction. I believe that this reaction is endothermic. So I think if you heat it up, it drives the reaction in this direction and it makes it more acidic. It makes the pH go down, making it more, I think that, but I'm not exactly sure. But yes, temperature does affect pH, yeah. It's just arbitrary. We just pick a number. Is it standard temperature? Standard temperature is 0 Celsius. It must be because that's the temperature at which most chemistry happens. Okay. You guys good on that slide? All right, guys, we're moving forward. This then brings us to this magic idea of Kw. So guys, we understand that Kw is hydrogen times hydroxide. This is all what we just talked about, but let's make sure. So guys, we've measured what Kw is. It's 10 to the negative 14th. But guys, this then becomes an interesting idea. Check this out. You ready to draw another beaker? Come on. Draw a beaker. So guys, here we got a beaker. Here we've got Wawa. Guys, what I'd like you to do is please draw in your beaker what's in your beaker when it's just water. Please draw in your beaker what's in your beaker. Now that you really know what is in your beaker, if it's just water. So guys, when this is just water, we should all be comfortable with the idea that there is water in water. But what else is in there? A little bit of hydronium, a little bit of... Let's do hydronium. Let's get rid of this. There's a little bit of hydronium ion. What else is in there? A little bit of hydroxide ion. Now guys, don't miss this. This is a big, many times confusing idea. Don't miss this. So let's talk about this. What is there the most of these three things? lots of water, right? Then, what do we know about the concentration of those two? They're equal. And we can then say that Kw, let me do this differently. I need a little more room. We can then say that Kw is hydronium ion times hydroxide ion. But guys, now we know Kw has a value. It's 1 times 10 to the negative 14th, and that doesn't change. So now guys, watch this. Let's dump some HCl into our beaker. We've already done this in another beaker. So guys, when we dump HCl into water, the chloride's a spectator, right? Let's not even talk about it. But where do the hydrogen ions go? They go to the water, and what do they make? So this breaks apart. Chloride is a spectator. The hydrogen, the protons latch onto the waters, right? What does that make? That makes more hydronium, right? But guys, as we make more hydronium, guess what happens? Hydroxide goes down. Why does hydroxide go down? Guys, it's Le Chatelier's principle. Let's do it the other way. So guys, this is all about Le Chatelier's principle. We've got water plus water makes can I do this? Is that okay? So guys, the idea is this. If hydronium ion goes up, what does Le Chatelier's principle say is going to happen to hydroxide? It's going to go down. But here's the thing that's cool. They go down proportionally. So as much as this goes up, this goes down, and Kw doesn't change. That's a little thing we like to call important. So guys, here's the idea. When we add acids to water, the hydrogens grab a hold of the waters and they make hydronium ion. Hydronium ion goes up, so hydroxide ion goes down, but now we can quantify that, and because Kw is literally a constant, these changes are proportional such that it still equals 10 to the negative 14th. Go ahead. That's a great question. Yeah. So say that again. So when we add hydrogens,
do those hydrogens favor making more hydronium ions versus bonding with hydroxide?
Yeah, good for you. So why does the hydrogen attack the water and not attack the hydroxide? And I'm going to answer it for you really briefly right now. Exactly. But when we get into chapter 17, we're going to start talking about buffers. And when we talk about buffers, we're going to get way more into this chemistry. But for now, it's exactly right that the water is more electron hungry or proton hungry, and it lands there first. We're going to quantify that in chapter 17. So guys, do you understand this idea of the idea that when we add an acid, hydronium goes up, hydroxide goes down proportionally, Kw doesn't change? So guys, what that means then is that if we have a water-based, acid-based solution, and if we know either one of these, we can solve for the other because Kw doesn't change. Let's say that again. If we know either one of these, we can solve for the other because Kw doesn't change. So if we know the concentration of hydronium, divide 1 times 10 to the negative 14 by that, and we now know hydroxide, and vice versa. So guys, you're going to be using this equation all the time. And the AP authors are really evil about this. They're going to give you a problem and you need to know the concentration of hydronium, but they're going to give you the concentration of hydroxide just to make sure you can do that simple math. They love doing this to you. So guys, we're going to be leveraging this equation all the time. So questions here? Okay, so then guys, the question becomes this. How do we actually measure the hydrogen or hydronium concentrations? And the answer is like this. Guys, this is how we measure these concentrations. We actually use what are called pH meters. You'll be getting them in lab, not next week, but the week following. But guys, notice that we have two forms of the pH equation. So let's talk about this quickly so that you understand what's going on. What does the H stand for in pH? Hydrogen. What does the P stand for in pH? Logarithm. Did you guys not know that P is the mathematical expression for logarithm? Then guys, we make these negative because most of the concentrations are smaller than 1. Guys, track with me here. If you take the log of a number that is smaller than 1, not negative, but smaller than 1, like for example, 1 times 10 to the negative 7th. If you take the log of a number smaller than 1, what is the value of that log? Negative. So again, and I know logs are a little tricky, but guys, if you take the log of a number smaller than 1, the value will be negative. So we just arbitrarily tag a negative on this just to make it positive because that's easier to work with. But then you'll notice over here there's another form of the equation that's hydronium ion. Do you understand that these are the same? We've had a long conversation today, guys, about sometimes we think about hydrogen as making hydrogen ion. Sometimes we think about acids as making hydrogen. Sometimes hydronium. We understand what it's always doing is making hydronium. It's just sometimes we don't worry about the water. Is that okay? Go ahead, Donnie. Then it is a dang kick-butt acid. But think about that. So if the log was, what would the value be of the pH? It'd be negative. And that's actually, so the strongest pH, therefore has the greatest negative number, is 18 molar sulfuric acid. And the reason that that's especially scary is because it's got 2 protons. But those have negative, so like 10 molar hydrochloric acid, which you use 12 molar. Let's do it. So the negative log of 12, right? Because this was the acid. I don't have my calculator. What's the negative log of 12? And you guys don't have your calculators? Oh, I have one on my phone. What is it? 1.08. So that is the pH of the acid you guys used in lab last time. It's negative 1. That's nasty stuff. Aminolikey. All right. So guys, with that said, then let's take a look. You guys are okay with this idea, right? Low. Don't miss this. Low pH is stronger acids, right? So guys, spend some time with me here. Because there is all sorts of interesting things going on in this table. And if I remember correctly, that's actually close to where we're at today. Yeah. I want something to write with. All right, so we're going to go here. Here. Okay, guys. What did you find interesting in this table? There's all sorts of stuff. Yeah. Lime water. Where is that? Oh, this guy. Do you know what lime water is? That doesn't mean lime like lime juice. No, lime. Say it again, Spencer. You know it. Calcium what? Carbonate. So lime is actually calcium carbonate. Yeah. I've never thought about that because really lime, the juice would be citric acid. Yeah. Guys, what else?
Because next time in lab we're using we're going to find the concentration of our blood, sweat, and tears.
Oh. Yeah. All right, so guys, let's pick this fruit and then let's get into the chemistry. So milk of magnesia is actually magnesium sulfate. They use it as it's for stomach discomfort. Maybe I'm going to guide the conversation. Guys. So, So guys, allow me, and I would strongly encourage you to write this down. First of all, and I'm going to zoom out a little bit more and clean up my mess. Man, my board is not enjoying me jumping back. You guys have it in front of you, so I'm going to stay zoomed out. Guys, allow your eye to scan down these two columns. Please try to identify the relationship between the numbers that exist in these columns. What is the, not add up, what is the product of these numbers always? KW. Guys, those two columns represent KW is equal to hydrogen times hydroxide. These two columns represent that. That as the hydrogen ion concentrate, guys, be careful. As the hydrogen ion concentration goes up, right? As we go down, these numbers are getting bigger by having smaller negative exponents. As the hydrogen ion concentration goes up, the hydroxide ion concentration is going down proportionally, always revolving around KW. Now notice this. pH is equal to the negative log of hydrogen ion. Guys, that's this. These exponents are the pHs. But in the same way that we can have pHs, we can also have what are called pOHs. In the same way that we can take the negative log of hydrogen, we can also take the negative log of hydroxide molarity, which are then these relationships. Or we could just talk about what milk of magnesia is. Guys. Then notice this. Water is in the middle, right? Water is in the middle, and then guys, down here we've got the dudes that are better at giving away hydrogen ion than water. Now we're switching to these molarities that would indicate more hydrogen than hydroxide, hydronium than hydroxide, and now we're talking about the acids. What do you think, y'all? There's, just a second, there's one other interesting thing that I'd like to point out to you. Guys, but I need to clean up my mess. If you wanted to write this down, did you get it? Okay, so do this. Talk to me about the numerical relationship between these. Not, well, kind of. They are conjugates, but mathematically, what will they always come to? Yeah, so 10 to the negative 14th as their products, right? Do you see the relationship between these two numbers? What's the relationship between these as you move down? They always add to 14. So pH plus pOH will always sum to 14. Guys, this is a direct result of this being true, where KW is 1 times 10 to the negative 14. If you understand enough about logarithms, this and this are necessarily true because of the laws of logs. But guys, fundamentally, you've got to understand that this is also true. pH plus pOH always equals 14. Find that on your equation sheet. Do you see it? You're okay? So guys, now we've got another equation that we can use to manipulate this stuff. Where is it? Oh, there it is. pH plus pOH is 14. So guys, now we've got another equation that we can use to manipulate numbers, because if we know the pH, we know the pOH, because they always sum to 14, which is simply what... We don't need to do this. Guys, that's simply what this is all about. And then we can bring these together and we can further talk about the idea that pH plus pOH is equivalent to 14. Now guys, one last thing and we're done. And it's simply this. We've already talked about this. What are strong acids? Strong acids or bases are things that completely break apart in water. So guys, one more beaker and we're done. You ready? Here's your beaker. And let's do this. Let's make this a 1 molar, let's make this a 1 molar HCl solution. So guys, in a 1 molar HCl solution, what's in there, and now how much? If you got a 1 molar HCl solution, what's in there and how much? So guys, obviously we've got some water in there. How much? A lot. But what else do we have in there? Do we have any hydrogen ion? No, because all of the hydrogen ion goes to water and it makes hydronium ion. But guys, what is the concentration of hydronium ion? 1 molar. Then we also have 1 molar chloride ion. But guys, this makes a really interesting assumption. Is this really the concentration of hydronium ion? No, because what aren't we accounting for? The hydronium ion that is formed by the autoionization of water. But guys, the deal is this. What is the concentration of the hydrogen ion from the autoionization of water? 0.00000001 molar. That's 1 times 10 to the negative 7th. So guys, this is the concentration of hydronium ion that's in the water before we add the acid. This is now the concentration after we add the acid, and it's 8 powers of 10 bigger. So we don't worry about this because compared to this, it's a rounding error. So guys, fundamentally then it's this. The molarity of a strong acid is equal to the molarity of hydronium ion. It's not exactly true, but it's close enough because the hydronium ion that comes from the autoionization of water is functionally 0. So guys, this then is your homework. So guys, as you're transitioning out the door, let me tell you right now, your homework assignments are going to be appropriately large. So guys, understand I'm not laying work on you just to lay work on you. These are things we've got to do. So for the next few days, your homework assignments will be a little bigger. Dig in and do them. And guys, we'll take a break and we'll be back after break. Ta-da! Bye, Michaela.